Hi, I'm Kwabena with OpenMV, and today I have Henrik with Alif Semiconductor.
Hi there, Henrik Flodell from Alif Semiconductor. Very good to be here with you, Kwabena.
Thank you. It's good to see you.
Good to see you.
Henrik, thanks for inviting me to your house. It's awesome to be out here. You have a gorgeous place.
It's my pleasure to have you here.
Yeah, no, I mean, and thanks for taking the time to talk to us about Alif. I mean, I think everyone wants to know about this new chip company. You guys are doing some amazing things with microcontrollers.
Thank you for acknowledging our efforts. No, I mean, we've been, how long have we been at it now? We've been at it since early 2019. So it's coming up on, well, it is 6 years.
6 years,
yeah. 6 years.
I know the pandemic, things just went through that whole time.
Time is difficult, right? But essentially what we wanted to do, most of us that were involved in, getting Alif started and that work for Alif, we've been in the silicon space for a long time. Mm-hmm. And we worked for, the usual suspects, the kind of people that are in most of the designs that are on the market today. And we kind of saw an opportunity being on the inside of those companies in that there tends to not be a lot of, very fast innovation because of technical reasons, because they kind of carry a technical debt in terms of, I've designed this one platform and I want to try to squeeze that for all that it's worth. And it's difficult to kind of move those silicon platforms onto, the latest manufacturing nodes or the latest architectures, use the latest tools, etc. once they've been established. And also you have a lot of backwards compatibility to
I ran into that. I used to do computer chip design at Oracle Corporation. And I remember you had your high level synthesis and then you had to use the primitives of whatever manufacturer you were using and you build that all into your code. And so it meant usually to throw away everything when you did a new chip a lot of times.
Yeah. So you go out and you talk to a customer and you ask them, so you're using this today. What do you want to use for your next design? And they go, I need this, and this. And it's like, I can't help you with that.
I see.
So we kind of noticed that there's all this new stuff that is really cool, available, but nobody's really using it. But we know how to make chips. So why don't we try to set up a new company, Alif Semiconductor? We try to pull in all of this great newness that is available. And we try to kind of skip a generation and go straight to what we call the next generation of microcontrollers, where we can integrate a lot more functionality at a lot less power consumption, and with a bunch of other, new cool features added so that people can make, even cooler stuff with these devices.
Yeah, I mean, tell me about the top three things that, Alif wanted to bring to the microcontroller market.
I'll tell you about four things.
Four things, okay. Cool.
So we wanted to make something that was truly scalable, because that's always an issue for people when they're like, you can't really go out with a single chip.
What does that mean?
So it means a couple of things. So some people, they try to go to market with a single chip that does one thing. We didn't want to do that. We wanted to go to market with families of devices so you can use us, for different things.
Okay.
But when people want to adopt a platform like that, I want to develop my software. Yeah. And then I want that software to be able to be deployed on the other derivatives of the device that you're making.
Sure. Yeah.
You can kind of look at some of the people in the industry today that have multiple families of chips, and you kind of, I write an application for this, it should be pretty easy to deploy that on the other thing, right?
Yeah, not true.
No, it is certainly not true. And we wanted to try to get at that problem a bit by making sure that we have an architecture that straddles all of these different derivatives that we're going to make software portability better. Yeah. And then also actually apply that to electrical compatibility, if you will. We wanted to try to have footprint compatible devices. So you can design for the footprint, and then, if I want to put a big one, I want to put a small one, whatever, just put it down. It will work. You have some more non-connects on the smaller ones, but, as long as you're using in your application resources that exists, across the parts, you'll be good. So that was one thing. We wanted to have that scalability. The other thing that we were really going for was low power, because we kind of look at the trend of the market in general, and wearables and those type of things, things that are battery powered, they are growing at a very, very rapid rate. As soon as there's a battery in the system, right, you want to keep that power consumption low so that you can ideally get, the benchmark from the customers we talk to seems to be about a week of use before you have to charge it. Yeah. So we wanted to get to a product that not only in a low power state, but also in active mode when you're actually using it, consumes as little power as possible.
Yeah, no, I totally get that. And we'll go into that later in this conversation, actually. There's a huge market for battery powered devices, not just for wearables, but for industrial systems and things that are deployed into the real world. But number three. So another thing that we wanted to do was that we wanted to put some security in these devices, because there are a lot of use cases now. It used to be traditionally that I have security because I want to protect the code that I put in the chip, the firmware.
I don't want that asset to be extracted and reverse engineered.
Yeah.
And then with the advent of over-the-air updates, it was like, all right, so I need to protect the asset, and I also want to make sure that I can verify the integrity of the update that I'm downloading, so I'm not breaking the device as I'm applying the upgrade. Now there is a lot more applications that deal with data that is being collected, in various contexts. It might be, if it's a medical device, it might be patient data. If it's a health tracker, it might be personal data to you. And people are now becoming more and more aware of the fact that, hey, I don't just need to protect the device itself. I need to also protect the data that it's processing, things like that.
Yeah.
And that can be a problem from a system perspective, if you kind of have to graft that onto a device that doesn't know anything about security. So we wanted to put a secure enclave essentially at the core of the architecture so that we could allow people to manage that from the inside. It just makes for a much tighter solution.
Yeah.
And then the fourth thing, and this was back in 2019, so I mean, people were still, they started talking about AI already back then, but not so much about AI in embedded systems. And we were kind of looking at figuring out, is there a way where we can get to running some of these machine learning models that are being deployed now cloud side natively on the embedded device, so that you can actually, with artificial intelligence help, process the data at the source where it's being collected, instead of just having to collect it and then send it up to a cloud and sit there and wait for the reply to come down with the radio on, consuming a lot of power through that entire process. So we just wanted to be able to enable getting results faster at the source, and to not only be able to do that with slow moving time series data, which kind of TinyML and those things were focused on at the time.
Yeah, but it's not, it's not going to be the future. Well, it's the future, but that's not sexy. Yeah.
No, but it's like, obviously that's needed, but it's like, can a microcontroller actually scale up to handle some complicated audio use cases beyond keywords, and also to be able to process video of some kind of frame rate, some kind of resolution. Right? That's what we were going for. And that is a market where we're seeing explosive growth at the moment in terms of just, the type of products that people are envisioning and the type of things that we, to some extent, help unlock for people to be able to achieve.
Yeah. No, it's actually why OpenMV, and we're doing this whole conversation, is because we found Alif's chip to be the best for this kind of application. It is incredible, I think, to look at the visionary step, I would say, of putting so much SRAM on your chip. So talk to me about that, because we look at other manufacturers, and I mean, there's a certain amount of stomach you have to do to be that aggressive.
Yeah.
I mean, I imagine back in 2019, there were people were thinking that was insane.
We did get some interesting feedback on some of those choices, but for us, I mean, the trade-off that you have to kind of look at is always like, if I put the memory in the chip versus if I use memory outside of the chip, am I saving money? But the way that we wanted to look at it was, what other parameters is it for the customers to consider? Yeah. So is it just about cents in the end, or is it also related to like the physical footprint of the system, right? If I have to put external memory in my system, and if that external memory happens to be of a type where, there are, let's say, particular design considerations to get it to work at, an optimum speed to the microcontroller, that might drive overall system size. And we wanted to help with that factor too, again, because of, things that are portable, things that are wearables. You might not have enough real estate to be able to fit something with a bunch of different chips inside there. The other thing was, we wanted to size the memory so that we could be kind of a truly one chip solution for an imaging pipeline that involves acquiring an image, storing that, processing it, and then also formatting it for being output to a display, and do that entirely within the internal system memory. Yeah. So that, for the most part, at least for kind of what we consider to be the sweet spot for our imaging capabilities, you don't need anything else. Yes. We have everything built in.
And so, to that point, here's the big reveal. I'd like to introduce the OpenMV AE3. Ta-da. So this is a new OpenMV CAM we built using Alif's E3 chip. And the incredible thing here is that this whole package is 1 inch by 1 inch. And so we were talking about a system that is small, that has a low amount, a physical footprint, and even make the system tiny. Having 13 megabytes of RAM on chip, which is, by the way, most of it is clocked at 64-bit AXI bus at 400 megahertz. So effectively 3 point something gigabytes a second on board. So that's basically DDR4 plus speeds as long as you don't go off chip.
Yeah. And that was another thing that we were, when we were doing the architecture, it has become a common trend for some where they kind of market, here is a clock frequency of the chip, but that's just a core.
Yeah.
Then the peripherals and everything else, memories, they run at some, divider version of that.
Oh yeah, absolutely.
And we wanted to be able to acquire data as fast as we possibly could. So it was like, let's just try to run everything at that maximum bus frequency.
Oh no, it's funny because there are some processors. A lot of times, I'll say it like this. There's a few. Let's look at the previous generation of microcontrollers that were at the 40 nanometer level. Our previous OpenMV cams, and there's some processors where you had big performance differences on M7 based cores.
Yeah.
Actually, because the system bus was different for different vendors. So you had some vendors that did 32-bit AHB, some that did 64-bit AXI, and some that did 32-bit AXI, but at a lower clock frequency.
Yeah.
And so because of those decisions, even though the core could be clocked at a really, really high speed, you saw very different performance levels on running neural network models, even the small ones on those chips and such. And so it's like, those small computer architecture differences really matter in being able to get the biggest performance or the best performance out of the system.
Yeah.
And they're not like top of the line specs, like everyone looks at the core frequency and says, oh, that's what's important. But if the core is attached to, if you have a 400 megahertz ESP32, but then you have, it's attached to a 8-bit or let's say a 1-bit octal SPI, 1-bit SPI flash externally,
exactly.
which has all your RAM in it.
That's the lowest common denominator in the system for moving data through.
Yeah,
right?
yeah, it really hurts you. And so having that internal bus frequency at a high speed, but of a high data rate, a high bit width is really the key there.
Yeah.
But that also comes with some really novel low power features.
Yeah. So the way that we set up the system internally with regards to just keeping power in check. And I mean, most people do this. We do a couple of things that are a little bit unique in that regard. We divide the functions of the chip into what we call power domains.
Yeah.
And then we can clock gate off either an entire domain or we can switch off peripherals as well if they're not needed. But essentially we've tried to partition the system in such a way that you can have a very fine-grained control over what is it that I need right now and what is it that I don't need. We've also implemented an API this is all marshaled by functions that are running inside our secure enclave to help people control the turning off or shutting down of these power domains in a somewhat autonomous way, depending on what it is that you need in the system at any given time.
Yeah, but it goes beyond that though, because I believe you guys actually on a clock cycle by clock cycle basis actually turn off bus fabric and other features that draw just a little bit of static power. But you do that every clock cycle, so it ends up being a lot.
Yeah. So I mean, because essentially when you look at power consumption over any duration of time, usually what you have to look at is like, what is the floor? What is the lowest amount of power that I'm drawing when I'm not doing anything, when I'm idling?
The static power draw.
Yeah, exactly, the static power draw. Because over time, that is going to be the biggest factor of power consumption for the most part in these systems. It's rare that it is the 100% CPU utilization part of your duty cycle that plays the most important role in the power consumption. So we want to try to squeeze that floor down as low as possible so that we can just run longer.
Yeah, but I mean, doing that though requires a lot of work because you basically need to design that from the get-go. This isn't something that you come in later and say, I'm going to add this feature.
It's impossible. It's impossible to do. It has to be baked into the system at the very core. So I'm happy that you acknowledge that, because it's one of those things that, I mean, I worked for some other companies where that has kind of been, well, let's not worry too much about that. It will be what it be when it comes out. But that's not the case. You're never going to be able to claim, ultra low power consumption unless you've actually made that a design goal to start with.
Yeah.
So that you can build a foundation that is low power and then put the rest of the stuff on top of it.
Yeah, no, so for the OpenMV AE3, we've actually hit some incredible power numbers on this guy. Yeah. So this whole thing, inferencing a model, running at about 25 frames a second or so, running YOLO, so full YOLO, 224 by 224, 25 frames a second. This is a YOLO nano model. Small models are a little bit slower. That's going to get you probably around 5 FPS or so, but nano. 60 milliamp current draw, whole system.
That's really cool.
Okay.
I'm impressed by that.
No, we didn't even believe the numbers because for every single previous OpenMV cam, we've always been above 100 milliamperes, like 160. So if you look at our OpenMV cam H7, for example, that runs at 100. If you inference on that, it's going to be 150 to 160 milliamperes full system draw, and you get about 0.3 frames a second. So 1 frame every 3 seconds or so.
Yeah.
And with this guy, we have 25x, well, more than that. It goes to 25 FPS, and our power consumption is now 3x lower.
Yeah.
So I don't have a calculator in front of me right now, but the last time I ran these numbers, it's something 400 to 500x improvement.
Yeah.
Which is 2 orders of magnitude. It is not.
No, it's not. It's. I mean, there's always some incremental improvements in things, but we're very happy, and I'm excited about this too. I mean, I've been plugging this for a while. I've been involved in the company since the inception and everything. But to kind of see, we had an idea, we had a vision for where we wanted our products, what we wanted the products to be able to do, and then to see how you've been able to realize that and what you were able to achieve with it. It's really cool. I'm super excited about, what people will be able to do with this when they pick it up.
Well, it is just, this is like, I wish it was a ChatGPT moment. It's probably not going to be that for us, but hey, maybe it happens. Never say never. But it is still, when you read startup books, a lot of them are like, hey, you need at minimum 10x, gain for people to be interested.
Yeah.
So what does 100x gain mean? And then honestly, what does 500x gain mean? Like, what does that unlock?
Yeah.
The beauty of this chip is that we're going to be able to realize now the ability to have cameras that can monitor, that can do analytics in any type of situation. So, there's most of this is just boring applications where you're staring at something and counting objects, but still that provides immense value. An example would be we have customers who have industrial equipment, and they have old gauges on that industrial equipment they need to monitor. And boring job, but it helps to know what the process values in a massive industrial system are, having those connected and uploading that data to the cloud. And you can do that using current ML tools on some of the current microcontrollers, but then you have more complex things, like maybe you want to measure heat gradients in some systems. You might want to have a thermal camera that you're running. But also, you need to be able to run on battery for a very, very long period of time. And so what this means is being able to go into a full power state, take some inference, and then go back into a low power state as quickly as possible is really the name of the game.
Yeah.
Besides for having the 60 milliamp current draw on this system, it's about 20 to 50 microamps when you're sleeping. And so again, that means, years of battery life if you have a system where you're able to throttle it between it's sleeping and then it turns on, takes a picture, runs inference, and it's off maybe let's say a 3 to 5 second on time, and then it does that every 10 minutes.
Yeah.
It lasts forever then.
Yeah. So that's another thing that we were, when we were designing this, the Ensemble architecture is a multi-core architecture. Yeah. So we have a couple of versions of the Ensemble devices that are single core part, but inherently the architecture was meant for multiple cores to be in the system. And we had kind of envisioned roles for these cores. Is this a core that is going to be always on, or is this something that we're going to spool off really quickly when there's work to do, and then we can shut that down? So for this guy, for the E3, there's 2 Cortex M55 cores in it. One of them is configured for efficiency, essentially. So we've used silicon gate technology and memory technology and things like that use as little power as possible in a standby mode on that side, and also, during the active mode of operation. So it doesn't run as fast. It doesn't run at the full 400 megahertz of the system bus on that side. But the idea is that you can keep that one on, and that can be collecting your data, and you will then be collecting data at a lower power than you would if you ran it on what we call the high performance core, the 400 megahertz core. That is the core that you would wake up when, hey, something interesting is happening. I need you to figure out what is going on really quickly. Yeah. And then once you're done, take the appropriate action, and then I can power you down, and then I can go back to running on the efficiency side of the part.
Yeah, no. To be clear, the 20 to 50 microamp number I was quoting, that is full system shutdown. Yeah. So wake up on a real-time clock interrupt or just eye open. But you're going to be in the 1 milliamp, well, hopefully, we haven't measured it just yet, but 1 milliamp or less, sub 10, I think, probably sub 5 milliamp territory for the system actually running in the mode Henrik just said, where we have it on and it's able to sense the world. And in this board in particular, we've actually hooked up the accelerometer and gyroscope, which draw about 600. I mean, if you're running them at low performance, they're less than 100 microamp draw. And then the microphone also, which in a low performance mode, it's less than 100 microamps. And so we have those both hooked up to the low power processor side, that high efficiency core, and you'll be able to actually run inference on that core at a low power and then wake up the main processor based on that. So this actually brings, and we hope to make it easy to use for our customers, to actually bring the real idea, this dream. And the dream has been, I want to make a system that maybe has a motion detection happens. And then it wakes up the high efficiency core, and that will then listen to audio, maybe vibration, and then based on that, it will then wake up the high power core. And this allows you to achieve insane battery life.
Yeah, and it's also one thing, some of the customers that we've talked to, they have, not specifically, for something like this, but, for other types of use cases that we support. But they have something in place today that is based on, hey, I have a controller here that is gathering the data and it's pumping everything up to a cloud. And then we have to sift through hours and hours and hours of data that contain no interesting information. It doesn't contain any of the stuff that we're really looking for. So just, kind of taking power aside, just to be able to do the figuring out, is this relevant? Do we need to pay any attention to this on the device and just filter all that out so that, the data that does go up to a cloud or, whatever it is that goes up, if it's just meta information based on the data, it just kind of pinpoints something exciting happened here that you need to look at, right?
Well, I mean, it's the same thing though. Like for this system, we have Wi-Fi and Bluetooth on board also, and so it'll be able to connect to the internet. But if you think about the power draw of Wi-Fi, for example, it's like in the 300 milliampere level. When you're
every time you have to turn the radio on, it's like kind of game over when it comes to low power, right? So you want to turn that on as rarely as possible in order to just sustain your battery life.
Now, I think we haven't mentioned this yet, but the low power piece is actually quite important. So when I go talking to customers, basically you have this kind of loop that people get into. You tell people, hey, I can do this cool analytics thing. Like we can put these cameras in your store and we can count people entering. Or we can count the idle time, or we can run some kind of model to detect XYZ, whatever analytics you want. And the customer's like, great, this sounds awesome. Okay, I've got some random security cameras that I have lying around that are pointed at the wrong angle and have bad resolution. It doesn't work to produce the best analytics. So then people who are more serious say, okay, well, we're going to run a new system and we're going to put new cameras in. And okay, that's going to require some conduit because we're professionals here. We don't just want to run PoE cable naked across the ceiling with zip ties. We're going to put this in conduit. But then that has to go somewhere. These cameras don't have NPUs on them.
No.
They all go back to a cloud.
It needs to go to a rack somewhere also in the store where, you can have all the data come in before you send it out.
And even then though, you think about the bandwidth of pushing this many cameras to the cloud. Now you have an internet bill that is no longer acceptable, and so what generally happens is customers are super pro this, and then they finally, you get to the end of it where you hand them the bill and you show them, okay, it's going to be this, we're going to get these analytics, but there's going to be $100,000+ install of this equipment to provide this piece of functionality. And unless the customer really cares about the analytics, you've just killed the sale. And it's not about the tech anymore at that, it's just the raw install cost. These are the problems people run into. And so battery power is critical to actually unblocking these applications. When you talk to somebody and say, yeah, you can just hook it up with 3D batteries, not even LiPos, non-explosive, standard alkaline batteries that cost literally $1 each, and say I can just put that in some plastic casing and then just have some VHB, sticky tape, and maybe one screw to hold it so that the sticky tape doesn't fail from gravity. Boom, you have a product then that can be deployed, and customers feel confident with that. They don't have to, raid the bank per se to be able to build this.
And it's also something, a system like that is also something that, on some level can be, if I can call it, serviced by people that doesn't necessarily need to be specially trained techs, right?
Yes.
Because it's like, if the light goes from green to red, replace the batteries.
Yeah.
You're done. Mm-hmm. That's it. That's all you had to do.
No, and it's very important. I think what this allows you to do is to make, a camera like this can become as ubiquitous as your smoke alarm. We can make systems that monitor analytics, and they're as easy to put into place as your smoke alarm, which runs off a 9-volt battery.
Yeah.
Now, these things do draw a little bit more power than a 9-volt battery, so I can't say that a standard a standard 9-volt battery is not necessarily going to give you the best battery life. But still, we want to get to systems that allow that kind of functionality, because this is where you can go really mass market, really deploy this in anything and everything imaginable.
Yeah. So one thing, tying into what you were saying just about, low power and, being able to be on for a very long time, like one thing that we are seeing is stuff like this, right? AR type implementation, where people essentially want to put intelligence into glasses, if it's prescription glasses or if it's sunglasses like these. And there are some inherent issues with that. I mean, we've seen some examples of people trying to do that way early, before, technology like this was available, and how clunky and frankly monstrous some of those attempts look like, right?
Oh yeah, I mean, you don't want it getting hot on your temple, no.
No, exactly. I mean, you need to fit a battery into it, you need to fit a processor into it, and then it depends, like, am I projecting images on the inside of the lenses? Do I have cameras built into this thing? Is there speakers? Is there microphones? Where does everything go? So to be able to get it down into kind of a physical size envelope where it actually fits, and then also be able to power it from a small battery, and to be able to keep weight down, because I mean, I have reading glasses, and if the reading glasses are heavy, and then it's annoying to wear them. And just imagine if I have to wear glasses like all the time. I think that the benchmark is around 35 grams for something to be comfortable on your face. And then just like you said, I definitely don't want the thing that sits on my face to have like, a heat sink or something attached to it. That's just a non-starter. So in order to be able to realize these kind of use cases, like you have applied this technology, that also gets very important to be able to just, make it do what it needs to do in as small size as is available.
Yeah, no, I wanted to talk about that actually, just briefly. See, this chip is 6 by 7 millimeters. We only realized this form factor of a 1-inch by 1-inch camera because of that. We actually had to push the tech pretty hard to build this thing. So this is blind and buried vias, all kinds of 3 mil traces and such like that. Surprisingly, the PCB, not that expensive though. You have to follow a very particular process, which I won't mention. But we got the cost of the PCB down to be a very low number. But it was really cool to actually push the tech to this level where we're starting to get towards like, I won't say iPhone level integration, but I like that we're kind of pushing all, O2, O1 parts and et cetera, and really packing an extreme amount of functionality into a tiny space. But one of the key things here is that we tried to actually do this before, early, like honestly, like probably 6 years ago with another chip. And we ran into fun problems. So when the power consumption is too high, the thermal envelope of these boards is not enough to dissipate it via convection.
Yeah.
So you actually run into an issue where it doesn't really matter if you have a small processor chip or whatever. If your system draws too much power in general, this board heats up. And it keeps getting hot until it becomes like on fire level, like you touch it and burn yourself. And we actually managed to achieve that. But never really, it was a non-released product because you were like, dang, touching this thing would burn you.
It sits on a table like this, and then you put it up and it leaves a mark.
Well, it's like this, like an example would be, sometimes you use an ideal diode, sometimes you use a regular diode.
Yeah.
The 0.6 voltage drop across the regular diode times the current, that's a certain amount of heat, wattage of heat that's being injected. And you may ignore, it's like, oh yeah, it's just a small number, but it's every second being injected into a PCB. Yeah. And if you don't have, that the PCB is tiny, it can't cool itself.
There's not enough surface area for that to go anywhere really.
Yeah.
It's just going to go up.
Yeah, pretty much. And so those are some of the challenges that, that are alleviated by having a system that can draw low power.
Yeah, that's true. That is very true. That's also something that everybody that is designing something small should consider.
Yeah. So, I want to talk about now, there's a few things that I wanted to mention that I think are really cool about your system. So besides for having an onboard NPU, which offers 200 gigaflops, so
there's actually 2 NPUs in this part, right? And combined, it's about 250. but 204, I think, giga operations per second on the
Main
high
core.
performance core.
Yeah, and then 46, I think, on the
46 or thereabouts.
Yeah, no, you can't combine them, and you wouldn't want to do that anyway. That just doesn't make any sense. But you have, what's really cool though is that there's this new processor called the ARM Cortex M55.
Yes, exactly.
And so this actually has something called vector instruction support, which is just like, you get the NPU and you get the vector instructions and you get the fast memory. It's like everything.
And you get the hardware support for floating points as well.
Yes, you get that. And so the Cortex M55, it's been very fun to learn how to use because it offers you the ability to do so technically it can do 16 8-bit numbers at once. For multiplying. That typically, though, comes out to be useless because you overflow your accumulators. But more useful is the 8 16-bit values at once. And so this allows you to go from the ARM Cortex M7 could double pump and do 2 of those in some situations to I can do 8 at once pretty much everywhere.
Yeah.
And so this gives me a 4x performance boost on pretty much any algorithm that I bother to actually port to Helium. I'm able to see that incredible increase in performance, and 4x is much higher than, increasing your clock frequency to 400 megahertz to 600 or whatever. That's not 4x performance improvement.
No, but it's to me it's also like you kind of look at Cortex M as an architecture.
Yeah.
In terms of where it has been and where it's going. It's kind of mature at this point. It's been around for a while.
Yeah.
So it is. I was surprised when we started looking into the data that ARM was showing us on the Cortex M55. We had to make a decision when we were establishing the architecture, what cores do we put in it?
Yeah.
And we looked at their data and we were like, this is kind of crazy if they can actually, if this is what they're telling us that it can potentially do, if you can realize that, just like you say, 4x is not 20% just by, upping the megahertz of the core. It's like, that's night and day for something that is as established at technology as it is. It's really wild. And the other thing that I think is kind of cool is that, like you say, if you bother optimizing for Helium, I know that it's not perfect yet. It will get better over time, but I know that all of the modern compilers that support the Cortex M55 by now, they have optimization switches that you can throw to have the compiler take a stab at doing that optimization for you. I mean, if you do it by hand, you're going to get better results always, but at least you can get, some level of performance even though you're not really spending a lot of time.
Well, I'll say this, GCC doesn't do anything, but LVM,
Yes.
LLVM, the ARM made that public now. It's free to use, and so we actually tried that out. It actually beats GCC by 20%, so a non-trivial amount. But then also I noticed that it actually inserts M55 stuff in for all kinds of random things in your code.
Yeah.
It's like if you do a for loop and it can figure it out, it just puts it into ARM55 for you. You don't have to do anything.
Yeah.
I wouldn't trust it per se to do that for anything critical. You still need to hand optimize, but still it's wow, it's just like all of a sudden your code is just going way faster randomly.
Yeah, it's nice. It's really nice. And then the other thing, there is support for hardware floating points in the M55 core as well. There is the Helium vector extensions.
It's actually going to do vector floating point too.
Yeah. And they've also managed to bring the power consumption of the core down significantly compared to the older generations, which is one of the things that attracted us to it initially. So for us, it was kind of a no-brainer. Also, we like the fact that ARM is really good at building ecosystems of partners and things like that. So in terms of software and stuff that is available that we don't necessarily have to make, but we know that people that are using our technology will want to use. There is other companies in the market today that will provide those services, and over time that will just get even stronger. So
oh no, absolutely. Well, I the reason I mentioned it's so important is because you can't expect the NPU to do everything for you. You need to have that ability to have glue logic to fix the missing things. And so for us, for example, we're actually doing debayering on the CPU, and we used the ARM Helium to do that. And I spent a lot of time, hand optimizing things, like not writing assembly, but the intrinsics, and then looking at the assembly output and being like, I can remove this instruction, I can remove that, and getting it down. And we're actually able to debayer a VGA image with bilinear debayering, and we're able to do that on the CPU core at about 6.5 milliseconds or though. it's enough that we can achieve 120 frames a second with VGA, and then that can be fed into the NPU. And you guys actually did something really nice here too. There's a GPU on board the chip. Yes, there's a GPU also, and so we can do the bilinear scaling on the GPU to take then that debayered image, scale it to the right neural network size, and then feed it to the neural network.
Yeah, we've tried to make sure that the GPU isn't limited to be used for the output path. So, I mean, it doesn't just render things to displays. Also, if you have image data coming in, it can be used essentially as an accelerator. And and then you can take advantage of helium on top of that. So
no, well, that's what we're using it for. Because when you have the full image come in, it's never the same size as what the network wants. And so it's obvious step. You have to do it all the time, but you can actually blow all your time in the rescaling operation. What we saw is that the Ethos U55 NPU, there's a network called FOMO from Edge Impulse, and that thing runs at 1200 frames a second basically on this, and that's up from maybe 10 or 20 on a H7.
Yeah.
So it's again like a ridiculously huge speed up for these tiny networks.
You just need to get a camera that can feed you images that fast.
Well, that's what we did here. See, this actually is a global shutter. So this the OpenMV AE3 will come with a global shutter sensor, global shutter color, and the sensor can run at about 100 frames a second at full res, and then 200 frames a second at VGA. But then it also has a special mode where you can put it into QVGA, and we can actually then go up to 400 FPS or so.
That's nice.
That said, though, the exposure is a problem there because the timing is so small then when you do that the camera basically can't see anything anymore. Everything's dark. But
it has some really bright lights behind the thing.
Well, there's actually the customers who want to use these kind of systems. They're actually typically doing like LED tracking, and so what they'll do is remove the IR cut filter from the lens, and then basically just track extremely bright lights. So it actually works perfectly for them.
There we go.
Because they're only looking for really bright lights in the first place. Yeah. But it's an incredible processor, and we're super happy to launch this and to bring the OpenMV AE3 to the market. So before we end this, I just want to ask, what are you guys thinking about the future? Where are you guys seeing things going? I know you just announced a new system.
Yeah, we are we did an announcement a couple of weeks ago about what we call Ensemble Generation 2, essentially. And you're familiar with the way that we name our parts. We have series of devices. We have an E1 series, an E3, an E5, and an E7. What we announced was what will become the E4, the E6, and the E8. And essentially, what we're trying to do is we're trying to deliver even more performance for these type of use cases, amongst other things by leveraging updated NPUs that can handle transformer type networks.
Okay.
So for machine learning, we're essentially able now to take advantage of context in addition to just being able to detect, what is in the frame. We can kind of look at what is there and what is happening, So we can start, or people that are using our technology can start designing use cases around those type of parameters. So if you think about like large language models, now you wouldn't run like, a full large language model on a microcontroller because they are very large indeed.
Yeah.
But there are versions that can scale down and they can run on more constrained systems so that, you can just essentially get a much wider range of AI supported directly on the device, directly on the edge, if you will. And in addition to that, we're doing a bunch of other things that we haven't really announced exactly how we're doing it yet. Just stay tuned, it will come out soon.
Yeah.
But we're also doing a lot of things inside the device to speed up the way that we move data through the system. So that we, when it comes to things like you're talking about, acquiring images and processing them, etc., that we can do that even faster.
Yeah.
And that we have even more hardware support for accelerating the typical type of functions that we've now noticed that our customers ends up having to, design software algorithms for, in addition to, what we already provide in software. So, and at the same time, we're trying to minimize the size even further.
So even smaller chips.
Smaller envelopes, yeah.
Yeah, no, we're excited about that because we'd love to do, we're just launching this now, so I can't say, when the Gen 2 of it, but assuming everything goes well and this is super popular, we'd love to keep the same form factor, but pack even more functionality.
That's right.
Anyway. Thank you for taking the time to talk with me, Henrik.
Thank you so much. It's been a pleasure.
All right.
I'm really excited to see what people will do with this, and I'm very happy to work with you.
Yes. Also, if you just want to get started with the Alif chip, Henrik, you want to talk a little about this?
Sure. So, I mean, obviously this, right? This is a really, really cool camera module, and you should definitely, check this out. This should be available for order. We sell evaluation boards for a lot of the different types of processors that we market. This is one of them. This is a dev kit. Just tries to bring out as many signals on this as we can, so that you can connect things, you can measure things, etc. We have other types of boards that are more oriented towards exploring from a software perspective. Things with cameras attached, things with microphones and displays and stuff like that. But visit your local electronics distributors. They have this stuff in stock, or go to alifsemi.com and you can find more information there. You can also order boards directly from our website. So, yeah.
Thank you.
All right.
All right.